All right. Today we want to look at calculation of deflection in trusses using the virtual works or methods. One may ask, what are trusses? A truss is a structural framework made up of straight members connected at joints, usually arranged in triangular units. Okay, yes, it is one of the most fundamental systems in civil engineering and also building construction and also building technology. Yes, because triangles are geometrically stable, meaning they don't deform under loads unless the members themselves stretch or compress. Exactly. Some key features of trusses are members, joints, loads, and also the triangles. Please take note that um, what we're having over here is a truss, okay, and we are being asked to calculate for the deflection at B, okay, exactly. Our topic over here says that we are calculating for the deflection in trusses using the virtual works or method. Okay. Uh-huh. So deflection is the displacement of joints in a truss under loads. Okay. Yes. Let's look at our question one and let's look at what it says. Our question one says that find the vertical and horizontal displacement at B using virtual works or methods. Take elasticity to be 200 gigapascal and area to be 0.000314 meter squared. Exactly. So this is our truss we are seeing over here that is having a total span of 6 meters and it's being supported by two supports, um, a roller at one end and also a hinge at the other end. It has a height of 4 meter and also a load of 10 kilonewton. This 10 kilonewton you are seeing over here is an external load. We are now supposed to discover the internal loads in the roller and the hinge support so that we can actually use them to calculate for our deflection. Exactly. So as we have the question over here, like the first thing we're supposed to do now is to pull down our given. We are supposed to pull down our given. So let's write our given over here and pull down our given. At this point, I will advise good students to take a calculator, a book, a pen, and a paper so that whatever we do, they can also follow. Yes, they can also follow. Also, don't forget to like, comment, and share. Subscribe for more also. Exactly. So let's proceed with our first question. And our first question says that we should calculate for the displacement at B. So let's calculate for the displacement at B and we don't know the answer. So let's put question mark over there. Let's put question mark over there. Exactly. So we don't know. And also, our elasticity is given to us as 200 gigapascal. So let's also put down our elasticity. Let's say this is our elasticity, 200 gigapascal. So our elasticity is equal to 200 gigapascal. 200 gigapascal, which is also equal to, okay. So let's put that down here manually. Yes. So which is also equal to 200 times 10 exponent 9. Okay. 10 exponent 9 Newton per meter squared. Okay. Newton per meter squared. What you are seeing over here is the same as but this is in Newton meter, but we actually want it in Newton millimeters. Okay. So we have to convert it. We have to convert it into Newton millimeters. So I'm going to rewrite that. And that is going to now become 200 times 10 exponent 9. Okay. Yes, times another 10. times another 10. You see, exactly. Exponent 6. Okay. In other words, if you see 10 kilonewton, or let me say 10 gigapascal, it is just the same as 10 kilonewton. Okay. So we can just write it as 10 exponent 3 Newton per millimeter squared. All right. All right. Also, our area is being given to us as this. So let's quickly put the area down too and see how best we can move. So this is our area, and our area is equal to 0.000314. Okay. Which can also be written as um let's say 200 or 3.14 times 10 exponent negative 4 times 10 exponent negative 4. 3.14 times 10 exponent negative 4. Okay. To convert that into millimeters, what are we going to do? Now you see that this is in meters. Okay. This is in meters. This is in meter squared. Exactly. So we are supposed to convert it into millimeters like this one. Uh-huh. So what must we do? We have to multiply it by 10 exponents. We have to multiply it by 10 exponent 6. Okay. Mhm. So that is, we are going to multiply this by 10 exponent 6. And now it's finally going to give us 314 millimeter squared. Okay. Exactly. Because it's an area. So what are we supposed to do next? Once we are done putting down our given, it means that um we can just draw a diagram and then we proceed. So let's all quickly draw the diagram together. Let's all quickly draw the diagram together. So this is the diagram that was given to us. This is the diagram that was given to us. So I think this is our B, this is A, and also this is C. We had a roller over here. We also have a hinge support over here. Yes. We learned some few months ago that roller support have one reaction internally, and also the hinge support have two reactions. Yes. So the whole span of this was 3. That is here was 3 meters, and this part also, let's say the whole span was given us 6 meters. 6 meters. The laws of physics are the same for all observers in uniform motion relative to one another. Okay, so please don't get confused. Don't get confused. Here is 3, and also here is 3, as you are seeing, 3 meters. So the summation of the two gave us that. So this was the height, giving us 4 meters. Let's put the height down so nicely. And then from here, what do we do next? We can proceed to solve our problem, okay? Can proceed to solve our problem once we are done putting down our details. So let's move to our solution. And this is our solution. This is our solution. Exactly. So now, no, we are supposed to calculate for our, but for the first time, because we are applying the principles of virtual works. It is composed of two. Okay, that is we have to do for the real and also the virtual. Okay, but first of all, let's calculate for the reactions. Let's calculate for the reactions. Okay, so due to that, we have to draw a free body diagram of this. Okay, and the free body diagram of what you are seeing over there is as simple as ABC, as simple as easy as ABC. So that is, this can be redrawn as this. And since roller has one reaction, I just put one reaction over there, and the hinge has two reactions, so we put two reaction over here. You see, so this is our 10 kilonewton, 10 kilonewton exactly. So we can put down our dimension. So here was 4 meters exactly, exactly. Do all to put down your free body diagram so that you don't lose the marks. So that you don't lose the marks. So let's label the parts. This is A, this is our B, and also this is our C. Exactly, exactly. So this becomes our horizontal force at A, and now okay, better still if that is the case, I could write them with different colors for safety reasons. For safety reasons. So let me name our reaction. So this is reaction A. Okay. Or you can say vertical force at A. This is at our reaction C. And this becomes our horizontal. So this becomes our horizontal force. Okay. This becomes our horizontal force at A. Uh, that becomes our horizontal force at A. So what do we do next? The next thing we can do is that let's just calibrate it. Let's calibrate it. So we can put here 3 meters as we are having over there. And also here was 3 meters. Okay, exactly. That is from if you draw this like this. Exactly. 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 Uh-huh. So we just have to calculate for our reactions. And once we are able to get our reactions, I think we are good to go. We are good to go. But I would prefer to use the vertical force. Okay, because they are all reactions. So if you say reaction, which one are you talking about? In this case, we're actually talking about the vertical force at A vertical force at C is this one too. So now let's proceed to do our calculation. But before that, we have to know our equilibrium conditions. Okay, so let's quickly put down our equilibrium conditions and then we proceed. So this is our equilibrium conditions, or better still, let's put them down this way for the equilibrium condition. Okay, so for the equilibrium condition, let's put them down this way. Exactly. And then for our equilibrium conditions, the first one, it can be denoted as this, or it is of three, as we learned initially. So the first one, sum of all forces. Okay, sum of all forces moving in the x-axis should always be equal to 0. Yes. Also, sum of all forces moving in the y-axis should always be equated towards 0. And also, for the I, we say that sum of all moments about a point should always be equal to what? 0. So these are our equilibrium conditions which we have decided to work with. Okay, so once we are done putting them down, let's proceed. First of all, let's calculate for the horizontal force. Yes, okay. Let's calculate for the horizontal force. So we're going to do that over here real quickly. So calculation of horizontal force. So let's say considering all horizontal forces. Considering all horizontal forces. Considering all horizontal forces. Considering all horizontal forces. Exactly. So in the consideration of all our horizontal forces, we are going to equate all our distance to 0. Okay, that is, we are going to use our initial rule. Okay, and the rule we are going to adopt is that what? The sum of all forces moving in the y-axis should be equal to what? 0. Okay. Finally, if we want to simplify that, that is going to be, but take note, look at something. For this problem we're having over here, and we know that this is our free body diagram. Free body diagram. This is our free body diagram. This is our free body diagram. Okay, so in this case, we learned that in physics, if you want to get the resultant vector, okay, uh, of forces, it means that you have to consider the ones that are moving in the same direction. You have to add it, and the ones that are moving in opposite direction, you subtract them. Exactly. So in this case, which forces are moving in the horizontal direction? Is the 10 kilonewton and HA that are moving in horizontal axis. So we are just going to add them. Okay. So after we are done stating our rule, we are just going to add HA to the 10. So we are going to write HA. Okay. Plus 10. Finally, we just equate it to 0. Okay. From here, what do we do? We are going to group like terms. So we can say that from here, therefore, our HA, our horizontal force at A, is equal to negative 10, negative 10 kilonewton, since it is a force. You see, very, 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 very beautiful. Uh-huh. From here, what are we supposed to do next? We are supposed to calculate for the vertical force at C. We are supposed to calculate for the vertical force at C also. So Let's quickly do that together. And for the vertical force at C, let's adopt a different method, and that is vertical force at C. Vertical force at C. Yeah, so this is our vertical force at C. Very nicely. Very, very nicely. So we are just going to pull down our rule and then so quickly. So we say that the sum of all forces moving in the y-axis. Okay. Because this time we're talking about vertical force. Okay, so the sum of all forces moving in the y-axis should be equal to 0. Okay, sum of all forces moving in the y-axis should be equal to 0. So from here, we are just going to simplify it. We are just going to simplify this, and then that implies that you see, because look at the problem we're having over here, and the moment we are going to be taking now, the moment we are going to be taking over here now implies that we have to multiply the, if we are taking moments at this part, assuming this is your origin and this is where you want to take your moment. Okay, so if you stand here with your compass, you realize that the moment is going to cause the 10, okay, to multiply this you are seeing over here. So the 10 is going to multiply the 4. The 10 is going to multiply the 4, as you are seeing over there. So this 10 will multiply the 4. Okay. Uh, and also, uh, our vertical force at C is also going to multiply the whole of this. Okay, the whole of this. So it's going to be VC times 6. VC times 6. As you are seeing over here, let's go and put it down together and let's come back. So, but in this case, the rule we are using is that we are saying the rule we want to adapt is that we are taking what anti-clockwise, or we want to take clockwise to be positive. Okay, so we are taking clockwise to be positive. We are taking clockwise to be positive. Okay. So if you are taking clockwise to be positive, what do that imply? That implies that um over here we are going to be getting minus 10 times 4. Okay, just as I showed you initially, plus RC, or let me say vertical force at C times 6. Okay, that is the whole span. Okay, then finally you equate it to what? 0. Then finally you equate it to 0. Finally you equate it to 0. What are we also going to do next? We have to also come and calculate for the reaction at what? Um, Vertical force at A also. Okay. But we can just adapt a very, very simple method to solve that too. And life becomes easier. And life becomes easier. Okay, so let's go and calculate for the vertical force at A also. And let's proceed. So, but before that, let's simplify this. Before that, this is going to give us what? Negative 40. Negative 40 plus 6 VC is equal to 0. Okay. Finally, what can we say? We can say that our 6 VC is now going to be equal to, because we have to move this 40 to the other side. So it's equal to 40. Let's repeat this one more time. Then now we can divide so that we don't lose the mark. So 6 VC is equal to 40. Then now let's divide fully. So we divide here by 6. We divide here by 6. Finally, this will take care of this. And you realize that 40 divided by 6. 40 divided by 6 will give you 6.66. But let's just maintain 6 decimal places. Okay. And this means that we are still going to be left with this equation. If we put asterisk over here, this is still going to be VC is equal to 40 over 6. 40 over 6, which is equal to 6.666666. Recurring decimal 6.6. Right, we want to just maintain 2 decimal places, so we say 6.67. Okay. Since it is a force, we name it as kilonewton. Then we are done finding for the vertical force at C. Okay. Let's also go and calculate for the vertical force at A. So over here, this is our vertical force at A. Vertical force at A. Exactly. Exactly. So in this case, we are just going to adopt a simple method to solve for our vertical force, and then we are good to go. So let's quickly do that. So our vertical force over here, our vertical force at A, we are saying that um we are still going to pull down our rule, okay, or our equilibrium condition, okay, and that is these forces over here. All forces moving upward will be considered as what? Positive. This is the one we want to adapt now, and that is what? Sum of all forces moving in the y-axis can be said to be equal to 0. Okay, you can equate all of them to 0, and then from here, but before that, why don't we write our rule coherently in a logical manner so that the meaning can be okay? So this is a positive reaction, and that is sum of all forces moving in the y-axis should be equal to 0. You see, sum of all forces moving in the y-axis should be equal to 0. Then from here, we are now going to use our initial rule we all know. That is, we are going to move all upward forces. You see, all forces that are moving upward, we will consider them. Over here, which rule were we using? This rule is actually supposed to be X. Okay, sum of all forces moving in the horizontal axis. So we say that sum of all forces. So this is positive, and this is sum of all forces moving in the horizontal axis. Sum of all forces moving in the x-axis should be equal to 0. Okay, Over here, what are we going to say? Let's write our equilibrium condition well. And this become, we are taking a moment to be what? Positive. That is clockwise. Okay. So that is sum of all moments. That is sum of all moments. Sum of all moments. Yes. About B. Yes. Should be equal to 0. That is the moment. Okay, we took it at A rather. So let's write A over here. Let's write A over here. So I think our equilibrium conditions are quite okay now. Quite okay now for us to be able to move on. Okay, so from here, let's rewrite this well. Let's rewrite this well. So for the vertical force at A, we can now compare the vertical forces. Look at the vertical force over here is VA and VC. So we say that VA is moving upwards. So positive VA, okay, plus which one again? Positive VC. You see, they are all positive. You can choose to write it or not. All is equal to 0. Now, if we know one, you can just know the other one by ease. By ease, yes. And that is this can find it because now we know that VA is equal to 6.67. We can put over here 6.67. 6.67 plus VC. Okay, is equal to 0. Finally, we can just equate to get our answer. Okay. Finally, we can equate this to get our answer. And that is, when we group like 10, we are going to get our VC to be equal to negative 6.67 kilonewton. So this is what the answer we are going to get now. This is the answer we are going to get now. Exactly. So from here, we are going to start taking it joint by joint, okay? But first of all, we want to consider the real system. And now we are done, let me say, calculating for all the reactions, okay? If you like, we can still redraw the, let me say, our beam again and even put the reactions around it, okay? Yes, to enhance understanding. So we are going to redraw our beam again and put all the reactions around it. So let's quickly do that together. So at the end of the day, this is what we had, and this is what we are putting over here. Exactly. So initially we knew that this is 10 kilonewton, and now this is B. This is A. This is C. Okay. Uh, so from here, we can now put our answers we had beside it. As simple as that. Here was 3 meters, and here is also 3 meters. This look like two right angle triangles. Exactly. So let me just pull down the reactions and we proceed. Over here, we had negative 10 kilonewton. So this was negative 10 kilonewton. And then for the reaction at A, for reaction at C, we had 6.67. That is 6.67 kilonewton. And over here too, we had negative 6.67, negative 6.67 kilonewton. Exactly, exactly. So let's put down our height. We can't do our well without our height. It's very essential in the calculation. So our height was 4 meters. Exactly, exactly. So we are good to go. So we are now going to start taking it from joint by joint. But first of all, let's consider the rail system. Okay. Because we have to, let's proceed. So first of all, we are going to take the rail system. Okay. So we are in the rail system. Let me write over here, rail system. So this is the rail system. Rail system. Since we said the virtual works method composed of two parts, that is the real works is equal to the virtual works. So we want to consider the real works first, and then we are going to know the forces at the joints. Okay, yes, we are going to know the forces at the joints. Then later we come and take the virtual works too, and then we see the forces at the joint. Later we are going to compare the two to calculate for our deflection at B. Exactly. So this is for the rail system. This is for the rail system. Uh-huh. This is for the rail system. So first of all, we want to consider joint A. Yes, we want to consider joint A. Uh-huh. So I'm going to write over here, considering joint A. So this is considering joint A. Considering joint A. Considering joint A. And then we proceed. Okay. And then we proceed. So if we are considering joint A, that implies that we have to redraw just that part. Okay, all the part that is affected by A, we have to redraw them again. So I'm going to put a diagram over here, and this is how the diagram is going to look like. So this is the angle over here. Mhm. The reaction we had was 6.67. Okay, I told you last semester that if you have something like this is your y-axis, this is your x-axis. Okay, here is positive, here is negative, here is positive, here is negative. Okay, yes, like that. If you transfer that knowledge back here, you are going to discover a lot. So just this alone, um, the answer we had here was this was point A. Okay, this was point A. There was a reaction over here, but you see that initially the reaction was this way, and we had what negative 6.67 kilonewton. That is negative 6.67 kilonewton. Okay. Uh-huh. You can choose to write it this way, or if you don't want to put a negative sign over there, you can just change this. Okay, if you clean this over here and you change this sign downwards like this, it means that you have to clean the negative sign too. Okay, yes. On this note, I continue to say that the laws of physics are the same for all observers in a uniform motion relative to one another. This and what we are seeing at the top over here, they are all the same thing. Okay. They're all the same thing. This one alone and that. You see, exactly. So just this one alone. Just this one alone and this. They're all the same thing. You don't get confused. So let's look at the horizontal force too. Let's look at the horizontal force. We can also rechange the sign of it. Okay. But we can just choose to maintain it that way. Okay. So this is it. 10 kilonewton. But it is negative. For this one, we don't want to change the sign, so we want to maintain it that way. So 10 kilonewton. 10 kilo. Negative 10 kilonewton. Okay. Negative 10 kilonewton. So we can put point A over there. Point A, since we know the value of A, we can just put it over there. So this is joint A. This is joint A. Exactly. This is joint A. That is joint A over there. We are seeing over there. Exactly. So we take this cardinal point also to very serious. We will be using it more often. Exactly. Exactly. So from here, if this is A, how can we name this part? How can we name this part? That is the next question. To be able to name those parts, it implies that one, initially from here, we know that this is what B, we know that this is C. But now we want to now uh, calculate for the what. We've just taken one part. Okay, see that this is, we've taken just this part alone. For this question, we've just taken just this small part alone. This is the part we want to consider. Okay, exactly as you are saying. So we want to just know the forces in that part alone. The part I've circled for you are seeing. We want to know the forces in just that part alone. So how are we going to name this part now? So this is going to become FAB. You see, so here is going to become FAB. Forces at AB, and here is going to become the forces at AC. I can re-put this well, don't get confused. And that's just going to make it become forces at. So this is it. And these are just the forces at. This is now going to become FAC. This is now going to become FAC. You see, exactly. Then from here, we can now still write our height. As we all know, this is the height. This is the height. This is the height. This is the height. So let's put the height down. This is 4 meters. This was 4 meters. Okay, exactly as we have done, as you are seeing over here. If you have any question, you can type it in the comment section. I'll be available to answer most of your questions for you. Okay, so let's proceed now to calculate for the force at what? AB. Okay, let's proceed to calculate for the force at AB. We're also going to calculate for the force at AC2. Okay. So don't worry. We are now moving. So, uh, first of all, what do we have to do? I want to show you something very, very, very important. Something very, very, very important. But before that, take note that I want to just draw a small diagram over here to display something, or better still, I can pick it from this page. I think that will be much more better. Okay, so let's say uh, what we are having over there looks like a right angle triangle. Yes, it looks so. If you consider right angle triangle, that is having an angle over here. Let's say theta. Okay, and maybe even here is your A. Okay, or let's say in this case you don't want to use AB. You want to just as it is being used like that. Okay, so you let's use it that way. You let's also maintain it that. So let's say here is our FAC. FAC. Let's say this is our FAC, and here it becomes our F. I'll name that later. Here become our F, AB, FAB, FAB, and then here, as you know, is already A. Since it is the origin, I can name it FAO. FAO. Okay, and I'll still be right. Don't get confused, and I'll still be right. But in subsequent ones, I will name it that way. Okay. Uh-huh. So, or better still, look at something. Let's just be dynamic in our work. So let me put over here FAO. Since this is the origin, we are considering as the origin. Okay. So you see the angle over here. Exactly. If you want to know the vertical forces, okay, and for this kind of strategy, if you want to know the vertical forces and also the horizontal forces, that is, let me say, FAB, FAC. What are we going to do, or what are we supposed to do? That is what we are going to discover now. Okay, so we are going to use our principle of that we know of SOHCAHTOA. So this is SOHCAHTOA. SOHCAHTOA. So this is SOHCAHTOA. So we have over here the SOHCAHTOA. Okay. Uh-huh. So SOHCAHTOA we are having over here implies that if we want to get uh, our horizontal forces, we have to use the cos. Okay. If we want to get the vertical forces too, we have to use the sine. Good students should have been able to write this down somewhere. Okay. So now we want to know the vertical forces in this kind of right angle triangle we are seeing over here. So what do we do? So we write over here vertical forces and we calculate for it. So this is vertical forces. Vertical forces. And the vertical forces, we are going to calculate for it very, very simple. That is for the vertical forces. We say we want to use what? Sine. Okay, so we are going to use so. We're going to use so, and so is the what? Uh, Sine. Okay, so we are saying that what? Sine theta. Sine theta is equal to opposite over hypotenuse. In this case, who is the opposite? Who is the hypotenuse? Uh-huh. So the opposite in this case become this part, and then the hypotenuse becomes this part. Okay, but take note, even before I put that down, I want to show you something. Okay, I want to show you something. So let me clean this. Let me quickly clean this, and then I'm going to also write for horizontal forces. And then for the horizontal forces, for the horizontal forces, for the horizontal forces. For the horizontal forces, we are going to use cos. Okay, that is, we are going to use K from the SOHCAHTOA I mentioned earlier. Exactly. So from here, what are we supposed to do next? I want to redraw this whole thing again for you to see something. Okay, don't get confused. I can redraw this in a certain way. I don't want you to get confused. Okay, so what this diagram you are seeing over here, it is the same as this two. So I just want to simplify it over here. Let me still use the same marker, and this is it. So from here we are going to say that um here our hypotenuse, we can write here FAB. See, this is the distance from what A to B initially, as you know. You see, then the next thing we can also do is that we can write here F um A FBC. I can write here also FBC. Then I can put over here FAO. From whatever I showed you over here and what you are seeing over here is the same thing. Don't get confused. Mhm. So the sign, if we are supposed to calculate for our sign from this, how is it going to become? Or our vertical force, how is it going to become? Okay, let's quickly do that together. So for the vertical forces, so we said that we are going to use the sign, and the sign is going to become what? Our sine theta is equal to opposite over the hypotenuse. Okay. But in this case, what are we going to say? We are going to say that our opposite is going to be what? F. Our opposite is going to be what? FBC. Our opposite is going to be FBC. And then our hypotenuse is going to become FAB. Okay. Exactly. Exactly. So I want to quickly rewrite this in a more simple form. That is, finally we can say that our sine theta, okay, our sine theta is equal to FAB, or let's say FBC over FAB. You see, our sine theta is now going to become what? FBC over FAB. Exactly. Don't forget to subscribe to my channel. Don't forget to like, share, comment for more. So from here, what are we going to say? We are going to say that if we want to get our FBC, okay, that is our vertical force, we can just say that FBC, we are going to do cross multiplication. FBC is equal to FAB, okay, times sine theta. Okay, so finally, answer that therefore our vertical force at BC, or our force at BC, our force at BC is equal to what? FBA sine theta. Exactly as you are seeing over here. So all this one I just did was for what? Uh, the vertical force. Okay, that is for the vertical force. So I'm just To avoid talking much, I'm just going to write over here hash vertical force, so that you don't get confused. Hash vertical. So this is the vertical force. So let's also go and do for the hash horizontal force. Let's do for the hash horizontal force. Okay. So let's do for the horizontal force also. And for the horizontal force, so we are going to use the cos. Okay. So we are going to use the cos. So the cos, in this case, we are going to say that our cos theta is equal to k, that is adjacent over hypotenuse. Adjacent over the hypotenuse. Okay. Uh-huh. So what does that imply? If we want to relate it to our topic of study, then we are going to say that our adjacent in this case is going to become our adjacent. Our adjacent in this case is going to become our FBO over the FAB. So let's quickly put that down together. As you are seeing over here, our adjacent K. This is the K we are going to use. As we want to know the horizontal forces. Okay, and that we have to use the cos. Okay, and the cos is equal to the adjacent over the hypotenuse. The adjacent over the hypotenuse. So let's go and do that together. So that is going to become FAO. Okay, all over the FAB. Finally, let's quickly rewrite this again. Let's quickly rewrite this again and see what we can produce. Okay, okay. So our cos in this case, our cos theta in this case, can be said to be equal to our FAO all over FAB. Finally, we can say that our FAO is equal to FAB cos theta. FAB cos theta. Exactly. So you can see the two equations we're having for the horizontal forces, the one we're supposed to use, and also for the vertical forces, the one we're supposed for the horizontal forces, we established and we had a rule of what we had this. Let me circle them for you to see. That is the first one. We had this, okay, FAB sine theta for the horizontal forces. For the vertical forces, okay, to calculate for the vertical force, we have to use FAB sine theta. Okay, to also get the horizontal force, we have to use what? FAB cos theta. FAB cos theta. So please pay attention to some of these things. You see this rule we have discovered, we just prove a rule. We are now going back to our whiteboard to proceed to solve our work. So this is where we were. This is where we were initially. We are going to be using those details in our calculations throughout. That is why there was a need to do for that. If you know it, you are good to go. Okay. So first of all, we want to calculate for AB first. Before we come and calculate for what FAC. Okay, we are still in the real system. We are still in the real system. Okay, at joint A. At joint A. Okay, so um we want to do calculate for FAB first before we come and do for FAC. Okay, then we are going to move to a different joint later. So let's proceed. So this is for AB. For AB. For FAB. For FAB. Uh-huh. And for FAB, um, we are going to consider all the forces. Okay, and we are going to and look at this is negative 6.67. Okay, because it's already moving down, we have to clean this negative sign. See, this is what I was saying. I just have to clean this for it to look equal. Okay, so now we can say that this looks equal to what you are seeing over here. Okay, so I just clean the negative sign. Because if it's pointing downwards, according to what we are seeing over here, if it is pointing downwards, then you have to clean the negative. But if you want it to point upwards, it means that you have to bring the negative sign back. That is why I clean it. So I think I mistakenly cleaned something else over here too. So let me just quickly put it back. Yes. So now I think our diagram is more fit. Okay. So this is 6.67, and because it's moving downwards, we have to consider that in the calculation. Okay, to avoid confusing a lot of people, let me just bring it back and maintain it that way, or let's just still be dynamic, but the real figure is negative 6.67. Negative 6.67. So now we want to calculate for our vertical force. Okay, we've calculated for our vertical forces. We know the vertical force in this kind of truss. This you are seeing over here. If you join the four to this, you see that it's almost going to look like a right angle triangle. What we just played with over here, plenty. Yes, it's almost going to try to look like that. So let's bring that idea back into what we are doing now and see how best we can be able to become learned. Mhm. So we know that the vertical force over here, the vertical force, we know it to be what? FAB sine theta, right? FAB sine theta. So what do we do? It is actually positive. Okay. So we are just going to add it. Okay. We're going to add it. FAB sine theta. FAB sine theta. FAB sine theta. You see, so what are we going to do? We said that if the forces are moving in the same direction, we add it. Okay, so due to that, to get the resultant force, we have to add them. Okay, so 6.67 plus, because this one is moving in the vertical direction. Okay, so let's also add the one that is moving in the vertical direction internally. Okay, so let's add it, and that is going to become 6.67, but not just 6.67, because it's pointing down, it means that it is negative. So I'm going to say that negative 6.67. Negative 6.67 plus FAB sine theta. FAB sine theta. FAB sine theta. FAB sine theta. Okay. Is equal to 0. FAB sine theta is equal to 0. But take note that why are we equating it to 0? It's because of the equilibrium conditions we learned earlier. Okay. Or better still, we could still put it down before we move to enhance understanding. Let me just put it somewhere here, and that is all forces moving upwards, sum of all forces moving in the y-axis are going to be equal to 0. Okay. So that is what we just did. That is all what we just did over here. So finally, but you have to know something, and that is this. So we said that, but I'm going to draw something over here to explain something before we move. That is but. You have to take note that the sign you are seeing over here, this sign you are seeing over here. Okay. But the sine theta, okay, or the which is also equal to the sine theta, which is also equal to the sine theta. Okay. I believe we all know what the sine theta is opposite over hypotenuse. It's equal to the h. Okay. It's equal to the h in this case, and then the h, or to get the h, you realize that according to Pythagoras theorem, the r squared is equal to what? The sum of the square of the other two sides. Okay. So that is our h in this case. Is actually what? H squared. Okay. If you want to consider this for the h, it means that this is the h over here. This is the h over here. And why are we calculating for the h? Because we want to know the distance. Okay. Good. You see this that we are having over here. This is 4 meters. Now we know that this is 3 meters. Yes, from here to here is 3 meters. Let me calibrate it. So from here to here is 3 meters. As we are seeing over there. 3 meters. So we know here is to be 3 meters. We know here to be, but we don't know here. You see this place. So the place that I've written with H. Let me write it with a blue color pen for us to understand something better. So this is the H I'm going to calculate for. See, by the H, we don't know the H, so we have to calculate for the H. We have to calculate for the H also. Very, very seriously. So the H, by the H is equal to what? X squared plus Y squared. Okay, that is the members in the x-axis, and then plus the members in the what? The y-axis. Okay. So the members in the x-axis in this case is, or let me say, the height times the base. Okay. So better still, I could denote it with different numbers. Okay. So if I say we want to calculate, we want to know the resultant, or look at something. If I'm saying that but, let me write this with a different color pen. So we are saying that But our so in this case, for our so in this case, our so we want to rewrite it well because you know that the so is equal to what? Sine theta. The so is equal to what? Sine theta. Sine theta, which is equal to what? Opposite over hypotenuse. Okay. So in place of the sine in this work over here, we want to just put opposite over hypotenuse over there because you know that the sine is also equal to what? Opposite of. So what can we do? What can we do? It means that we have to look for the opposite over here and we also look for the hypotenuse so that we can eliminate the sine from our calculation. Okay, that is the main reason why we are doing all of this. Okay, so the opposite we know to it to be 4. Okay, but this h, we don't know the h. This h, we don't know the h. Okay, so to find for the h, that is why I'm going to use the Pythagoras theorem to calculate it because this over here, it looks like a right angle triangle. So if I want to get the h, I can use the formula that we know it to be what? R squared is equal to what? Or let me say a squared is equal to b squared plus, you see, we can also adopt that formula. I believe we all know this formula. That is what? A squared is equal to b squared plus c squared. This is the formula we are going to adapt over there. Okay, at the end of the day, when we root both sides, the square root will affect everybody and life becomes much more easier. So let's adopt that. So in this case, this is our h we are talking about. Our h is going to become equal to this. H is equal to x squared plus y squared in this case. Okay, and who is our x? Who is our y? Our x is 3 meters and then our y is 4 meters. You see, so it's as simple as that. It's as simple as that. So finally, we are saying that our h is equal to 3 squared. No, but you see, at the end of the day, all these people have to be rooted. Okay, so after this, I will do it for you to see. Plus 4 squared. And they are all affected by a root sign. They are all affected by a root sign. They are all affected by a root sign. Uh-huh. Yes, exactly. So from here, let's all quickly point this together. If you point, you realize you're going to get 5 units. When you point this together, you're going to get 5 units. So this is going to give us 5 units. Anytime you do a square root, your answer is going to become plus or minus. Okay, but we want to adopt the positive for this our calculation purposes. So 5. So now we know that that distance is 5. So now we know that the h over here, we know that the h is 5. You see, so I can now clean it and write 5 over there. Don't get confused. Don't get confused. So I'm just going to clean the h over there and I'm going to just write 5 since we now know that it is 5. Let me write it with a blue color pen so that you don't get confused. Better still, I can clean all of them within and make all of them coherent. Yes, so that is what I'm going to do now. So I'll take off this one, take off this one too. And then I'm going to write it. This is 5 meter now. uh This is also 4 meters. And now we know that this is also 3 meters. Exactly. You see what we are having over here now? So we can now proceed with our work. So finally, we can finalize this one over here and say that now the opposite is what? 4. You see, it's 4. And now the h is 5, just as we just calculated for. So we can use that in our calculation. So that in place of the so, I'll put that over there. I'm going to repeat that step one last more time, and then the life becomes easy. Okay, so Let me quickly repeat that step one last more time and then we go. We said negative 6.67 plus FAB FAB sine theta. FAB sine theta is equal to 0. Good. So from here, it's just a matter of substitution. It's just a matter of substitution. Okay. So, but this over here, once I put it into brackets, you should know that something is happening to it. So now in place of here, we can put uh, 4 over 5, as you saw. So I'm going to rewrite this again. So this implies this is going to become negative 6.67, okay, plus FAB. FAB into brackets 4 over 5. 4 over 5. Or is equal to 0. Quickly punch 4 over 5 inside your calculator and tell me the answer. 4 divided by 5, you are going to get 0.8. So in place of that, we can use a 0.8. I don't like it, so I'll use a 0.8. So I'm going to rewrite it again. So this is now finally going to become negative 6.67 plus FAB FAB, and I put it into brackets 0.8. So this is 0.8. Okay, I equate all of this to 0. So now I can just find for my FAB by grouping like terms, you see. So let's quickly all do that together. So this is now going to make my answer to become FAB. FAB, and that is 0.8. 0.8 is equal to, if you cross the equal to sign, you are going to become positive. So because it's negative over here, so this is now going to become 6.67. Let's repeat this step one last more time again, then we can divide. So this over here, always remember to write the numbers before the alphabet. So this multiplying this is going to give us 0.8 FAB. FAB. Is equal to 6.67. So we can now divide. I'm going to divide here by 0.8. And I'm going to also divide here by 0.8. 0.8. So let's quickly cancel out. This will take care of this. And finally we are left with our FAB. Finally we are left with FAB. FAB is equal to 6.67 all over 0.8. Yes. So let's all do it together. 6.67 all over 0.8. And what are you going to get? You're going to get 8.33. Okay. So that is 8.3375. So let's simplify by writing answers. It's just two decimal places, 8.34 kilo Newton. kilonewton. Then from here, we are going to also calculate for what? You see that we've calculated for FAB. So let's get that calculate for FAC. This FAC. For now, we'll not waste much time because most of the work has already been done. Okay. So once we are done calculating for FAC, we also calculate for FBC, and then the only thing we do now is go to the virtual. Yes. So we are coming to calculate for, we are still on joint A. So we are now coming to calculate for FAC. So let me write over here FAC. So this is for FAC. FAC. Okay. So all for AC. This is for AC. For FAC. So we are now coming to calculate for FAC. So let's quickly do that together. We did the same thing for this already too. So FAC, let's quickly do that together. Better still, I can put some asterisks to denote it well to avoid people from getting confused. These are the ones we are going to be using. So I'm going to also put an asterisk over here so that understanding can be more alright. So let's proceed. So for FAC, it means that this time we are going to calculate for the horizontal, let me say horizontal force. Okay, FAC, FAC. Because we are calculating for the horizontal force. Okay, we're going to calculate for the horizontal force. So this is it, FAC, FAC. Okay, so for the FAC, how do we go about it? It's the same thing. Look at our problem over here. You see the problem we are having over here. Who are those moving in the let me say the x-axis? 10 is moving in the x-axis. Negative 10 is moving in the x-axis. Also, our FAB cos theta as we learned initially. You see the x-axis, or you see this one, the horizontal axis or the x-axis. Yes. So the formula for that is what? FAB cos theta as we learned initially. FAB cos theta. Okay. So converting that knowledge to this, it means that we have to add the negative 10 plus what? FAB cos theta. Okay. Yes. Plus the whole of FAC, the force within that again. You see? Uh-huh. So that is going to become this, the whole of FAC. If I say plus the whole of FAC, the whole of this. So we are going to be getting negative 10. Okay. Plus FAB. FAB. That is, we want to know the horizon, the force that are moving in the x-axis. Okay. Why didn't we put down our rule? Then let's put down our rule so that the rule can guide us. So that the rule can guide us. Exactly. So this is for the x-axis. We are considering all forces that are moving towards the east to be positive. That is sum of all forces moving in the x-axis should be equal to what? 0. So now we can proceed. So see, The negative 10 there, it was already negative, so don't worry. So we say negative 10 uh-huh, plus FAB cos theta. FAB cos theta. FAB cos theta. FAB cos theta plus FAC plus FAC. At the end of the day, we equate all of this to 0. At the end of the day, we have to equate all of this to 0. The cos, what do we know about the cos? We learned something, and what do we know about the cos? We can apply that knowledge. Okay, so let's quickly write that, and then we proceed. So this can also be written in this way: negative 10 plus negative 10 plus FAB, FAB. Okay, exactly. Instead of the cos, we know that the cos is equal to the car. Okay. This is it over here. This is what I'm talking about. And the cos is our car in this case. And that is equal to our cos theta. Our cos theta, which is equal to adjacent over hypotenuse. Adjacent over the hypotenuse. So in this case, our adjacent is 3. And then our hypotenuse was 5. Yes, our hypotenuse was 5. So that is what we are going to put in there. As simple as that. As simple as that. So I'm going to write that quickly there. So in place of this, so in place of here, I'm going to now write, let's say, 4 over 5. 4 over 5 plus FAC. We don't know FAC. So that is who we have to look for now. FAC is equal to 0. What do we do next? We just have to group like terms and see how best we can become history. So let's quickly do that together. And grouping like terms, that is, first of all, let's simplify this. And this is going to give us negative 10 plus FAB. FAB. But 4 over 5, when you punch 4 over 5 on your calculator, what are you going to get? 0.8. Okay. But in this case, is it 4 over 5? We're actually using 3 over 5. Okay, so let's actually use the right figures. Let's put 3 over 5. So this is 3 over 5. So the 3 over 5, let's punch 3 over 5. You're going to get 0.6, and 0.6 is what we are supposed to be using inside there. If you like to better still, you can maintain it for your calculations, and life is still flexible that way. Okay. But before that, I want to draw your attention to something. I want to draw your attention to something. And that is, you already know that FAB, you already know the value for FAB, right? And FAB was what? FAB was 8.34. 8.34. So if FAB is 8.34, why don't you just simplify it straightforward? Then this is negative 10. Okay. Now anywhere we are going to see FAB, I'm just going to put 8.34 over there. So plus 8.34. 8.34. Okay. multiplying 3 over 5, okay, plus f a c plus f a c. Finally, what are we going to get? Let's equate this to 0. So this is a matter of simplifying. Let's quickly simplify over here before we even group like them. So negative 10 plus 8.3, 4, multiplying, let's say, 3 over 5, multiplying 3 over 5 plus multiplying 3 over 5 is okay. So what are we going to get? We're going to get negative 4.996. So that is negative 4.996. Okay. Plus F is, this is the answer we are going to be getting. Let's equate this to 0. So from here we can group our like terms and life becomes much more easier. So we can say that finally our FAC is equal to, it's going to be positive, of course. So you're going to get 4.996. Not just less, it's supposed to be in kilo Newton. It's supposed to be in kilo Newton. But this, why don't we just convert it into a whole number? Okay, that is finally we can say that therefore, therefore our force at F, our force at what? FAC, FAC is equal to 5 kilonewton. 5 kilonewton. Okay, as simple as that. As simple. So now we are done doing for let me say FAB. We are done doing for FAC. We are now going to do for FBC. We are now going to do for FBC. You see, that is, but to get the FBC, we have to go and consider joint C. We have to go and consider joint C. Because we have already considered joint A. Can you see over here? When we took joint A, when we took the joint A, you see that first of all, we calculated for the reaction, all the reactions. Okay, for that one is basics. Then from the reaction, we focus on joint A to calculate for the reaction FAB and FAC. You see, you could have also focused on just joint C to calculate for what reaction FAB and FAC. But this approach, I like this approach. That is why I'm using the joint A to calculate for FAB and FAC. Do you understand me? So now I can't use this to calculate for FBC. I have to now go and take or consider joint C. You see, then I can now use the joint C to calculate for the FBC before I can now move to my virtual works. So I'm going to write considering joint B. I'm going to write considering joint B. I'm going to write considering joint B and then we proceed from there. So over here, this is considering joint B. So we say considering joint B. Considering joint B. Considering joint B. Okay. Not just any joint, but to make it look more professional, then I want to change color pen and then write it in so that at least everyone can know what we are talking about. So this is the joint. This is the joint. So we're actually considering the joint A. Over here we consider the joint A. Over here too, we are going to consider the joint C. Over here we are considering joint C. Joint C. Considering joint C. So we are going to redraw the whole diagram again. So we are going to redraw the whole diagram again. And you see how we are going to draw joint C to be able to do our calculations effectively. So this is our joint C to calculate for our FBC. This is how our diagram looks like for that. So this is our FBC. FBC. FBC because you realize that our B is at this side. So we are considering joint C, okay. So this is our C. Let's put a C over here. Let's put our C over here. This is our C over here. Okay. Let's put on the reactions. So this is our reactions. This is our reactions, okay. And for our reaction, as you know, this was 6.67 kilonewton. 6.67 kilonewton. Our angle is here, as we know. Here is 5 meters. It's equal for all. Don't get confused. So here is 5 meters. And this becomes the 3 meters. All of here. You see. So FBC, because we can't say that the language will not be too proper. FCB. Okay, let's say FCB. You see, it won't be coherent. So that is why let's have to say FBC. Okay. So we say FBC. And here can be FCO. Then we can say here will be FCA. But we've already know FCA. We already know the FACO, so FCA. This one. This one is, let me use a green color pen to denote it. You already know this one already. This is FCA. FCA. And this is going to be what? FCB. I'm bringing the C first because I want your focus to be more there so that you know that that part, okay, is the joint we are focusing on. That is why in numbering, I brought it first. That is why in numbering, I brought it first. Oh, that is what, yes. So let's proceed. So I'm going to put my height over here. I'm going to put my height of 4 meters over here. So this is 4 meters. This is 4 meters. This is 4 meters. Exactly. This is 4 meters. So from here, the same procedures we adapted, we're going to use them to calculate for our joint C. At this point, my name still remains Megabyte, the physicist. Don't forget to see me in groups in person in case you find any challenges related to whatever we have learned. Meet me in the part 2 of this video, and then I will make you history on how to calculate for the FBC and also how to use the virtual method in continuing the rest of the calculation to even finally arrive at your deflection at B. At your deflection at B. Also, don't forget to throw $1 on my name if you find this video very, very, very interesting. Yes. Thank you very much. Meet me in part 2 of this video for you to become more learned in history.